All right, if you're an AP Physics student, you know friction is a huge topic. But today, we're going to do more than just look at formulas. We are going to unpack the story of static friction, that invisible force that, honestly, keeps our whole world from just sliding apart.
You've been there, right? You're trying to move some heavy piece of furniture, you're putting your whole back into it, and nothing. It just sits there. So what's going on? Well, you've just come face to face with the hero of our story today, static friction.
So what is this force, really? You can think of static friction as the grip between two surfaces. It's the floor pushing back on that box, and it perfectly matches your push to keep everything totally still. Without it, you couldn't even stand up straight. It would be like living on an ice rink. Okay, let's visualize this. Imagine you just give that box a little gentle nudge. Your applied force is that small arrow pushing to the right. And look at that! Static friction instantly responds with an equally small force pushing in the exact opposite direction.
Because those two forces are equal and opposite, they completely cancel each other out. That means the net force on the box is a big fat zero. And we all know what Newton's first law says. An object at rest stays at rest, so that box isn't going anywhere.
So what happens when you push harder? You really lean into it. See how the arrow for your applied force gets bigger? Well, look what static friction does. It gets bigger too, matching your push perfectly, Newton for Newton. And the result? Still nothing. The box stays put. This is what makes static friction so cool and kind of weird. It's not one single number. It's smart. It adapts. This idea of an intelligent grip is the perfect way to think about it. It just holds on tighter and tighter the harder you push.
So here's the first big rule you need to remember. As long as that box isn't moving, the force of static friction is always exactly equal to the force you're applying. You push with 10 newtons, it pushes back with 10. You push with 50, it pushes back with 50. It's a perfect balancing act. But that brings up a really obvious question, doesn't it? Is there a limit? I mean, can this force just keep getting stronger forever? If it could, you'd literally never be able to move anything.
And of course, the answer is no. Every grip has a breaking point. Just like you can't hang from a rope forever if more and more weight is added, static friction has a maximum strength. There's a point where it just can't hold on any longer.
We call this limit maximum static friction, or FS max. And this is really important. Unlike that adjusting force we were just talking about, this is a specific fixed value. It is the absolute tipping point you have to overcome to get that box to finally slide.
So how do we figure out what that breaking point is? Well, for that, we have our master formula. The maximum static friction equals a funny-looking Greek letter called μs multiplied by the normal force, which we represent with a capital N. Let's break down what those two things are. It's really just a two-step process. First, we've got to find that normal force, N, and second, we need this thing called the coefficient of static friction, or μs. Okay. Let's start with the normal force. It sounds complicated, but it's not. It's just the support force the ground pushes back up with. On a simple flat surface, the normal force is just equal to the object's weight. It's literally the force that keeps the box from falling through the floor. And next, we have μs, the coefficient of static friction. This is just a number, with no units, that tells you how sticky or rough two surfaces are together. The higher the μs, the more grippy the surfaces are, like sneakers on a basketball court. The lower the μs, the more slippery they are, like skis on snow.
And this chart makes it super clear. Look at rubber on concrete, a coefficient of about 1.0. That's a huge amount of grip, which is why your car's tires work so well. Now compare that to wood on wood, which is quite a bit less. And then you get to ice on ice. Look how low that is, almost no grip at all. Okay, let's put these two ideas together. And I'm serious, if you're an AP Physics student, this is probably the most important thing to understand about this topic, the difference between the adjusting force and its maximum value. Let's make this crystal clear. On the left, you have static friction, Fs. That's the variable force that matches your push. It can be anything from 0 up to its limit. On the right, you have its maximum value, Fs max. That is a single number, a threshold that you calculate with the formula. The actual static friction can be any value, as long as it's less than or equal to that maximum.
So, to wrap it all up, here are the three things you have to remember. 1. Static friction is smart. It adjusts to whatever you're doing. 2. It has a hard limit, a maximum value, Fs max, that you can calculate. And 3. To finally get something to move, your applied force has to be just a tiny bit greater than that maximum value.
So you did it. You pushed harder than FS Max and the box is finally sliding across the floor. But what happens to friction now? Does it just go away? Or does it maybe transform into something else? Well, that's a story for next time.